Still on already?
One second, let us wait for some people to arrive to connect.
Wait a bit, yeah.
Okay, welcome everyone to this 7th episode of the Mid-Infrared Discussion webinar series. I am Simone De Liberato, and together with Vincenzo Giannini and Stefan Meyer, I'll be your host today. Just a few words of introduction. The MIDI webinar series aims to offer the different communities working on mid-infrared nanophotonics an opportunity to showcase results and foster collaborations. This first season, which concludes today, was in our opinion a success. We had great talks and very positive feedback from the community. We thus decided to organize a second season covering a broader range of mid-infrared nanophotonic platforms. The second season will start on the 1st of October. All registered participants will receive an email in due course. Some institutions asked us to provide attendance certificates in order to validate the MIDI webinar series within their graduate curricula. During this first season, we provided such certificates on an ad hoc basis. For the second season, we will attempt to provide the service in a more structured way. So should this be of interest, please ask a representative of your institution to contact us. Okay, now back to today's webinar. We are glad to have with us for the season's finale, Professor Chijie Wang. Professor Wang is a full professor and associate chair at the Nanyang Technological University in Singapore. He is an OSA fellow, and he was the recipient of the Singapore Young Scientist Award in 2014 and of the Nanyang Research Award in 2015. Some practical information before leaving the virtual floor to Professor Wang. The talk will last roughly 45 minutes, followed by time for questions. In order to ask questions after the talk, you can use the Q&A button on the Zoom interface. You can either just write voice and I'll unmute you and you will be allowed to ask your question, or if you prefer, you can write your question in full in the Q&A box and I will read it aloud. Please note this webinar will be recorded and it will be shared online later during the summer, including questions. Okay, I'm done. I let Professor Wang start his talk.
Okay, thank you, Simon, for the introduction. First of all, I want to thank all the organizers, Simon, Vincino, and Stefan, for giving me this opportunity to talk about our research related to mid-infrared photonics. Okay, so I'm going to show you the presentation slides. Can you see my slides?
Yes, not full screen though. Yes, perfect. Okay.
Good morning, good afternoon, and good evening. I know participants from all over the world. My name is Wang Chijie. I'm from Singapore. So today I'm going to share with you our recent results related to mid-infrared photonics in two-dimensional materials. Particularly, I'm going to talk about two main topics related to mid-infrared photodetectors and highly confined Phonon-Polaritons in two-dimensional material in the mid-IR. Okay, before I start my presentation, I would like to thank my collaborators, particularly Professor Liu Zheng from Material Science Department at NTU, who provide many of the 2D material samples to us, and also Nikolai Zadlov from University of Southampton, who collaborate with us on nanophotonics research topics, and Professor Tom Wu from University of South Wales, Sydney, who collaborate with us on one of the mid-infrared photodetector samples that I'm going to present soon. And I would also like to thank my group members, including a few PhD and research fellows. And particularly, I want to highlight, give a special thanks to Dr. Alexander, who is the leading and the key person to drive the research on highly confined Phonon-Polariton work. and Dr. Xue Chao, who was my PhD student now at Cambridge University, who is the leading author, the person for the development of mini-infrared photodetector in 2D materials. Okay, so this is the spectrum of the electromagnetic wave and in the electronics. So the electronic devices has been well developed with go high frequency device go up to 1 terahertz, and for photonic devices you can go from shorter wavelengths into the longer wavelengths up to 3 micron using diode lasers. However, there's I would say called relatively gap in the mid-infrared and the terahertz region. That is still lack of high performance, photonic devices that can be used to build the high performance system. And one key component I would see for the mid-infrared and the terahertz photonics is about quantum cascade laser. That is a semiconductor-based device that can cover, based on the design and from roughly from 3 to 300 micrometers, almost a whole unit range. In the mid-infrared terahertz. And today, the focus is on the mid-infrared, and this is so-called the fingerprint region, roughly covered from 3 to 20 micrometers. And there's many unique applications. For example, many moleculars, like a gas molecular, has very unique and strong absorption features in the mid-IR, here in this spectrum from 3 to 40 micrometers. Therefore, it can be used for sensing spectroscopy application, countermeasures for defense application, where high power light source is able to use to diffuse the missile tracking. Chemical weapons, LiDAR application now can be used in satellite communication or in emerging application like autonomous vehicles, because it's better than the near-infrared LiDAR system. Because it can propagate longer distance because of a longer wavelength. Okay, so other applications include breath analysis, free space communication, environmental monitoring, industrial process control, and so on and so forth. For free space communication, I want to highlight that because the mid-infrared wave have a long wavelength, therefore it can propagate a longer distance, and there are 2 transparent windows in the atmosphere. One from 3 to 5 micron, and the other is from 8 to 12 micron. So light can propagate relatively longer distance in this case. And in terms of device development, of course, in terms of lasers, QCL has been well developed based on 3-5 compound semiconductor, fiber lasers based on superconductor generation, soft glass fiber can produce ultra broadband coherent light source covering a very wide range in the mid-IR, and solid state laser by using new crystals like gallium selenide. It can also be used to develop ultra fast high pulse energy laser source. In terms of detectors, MCT detector has already been widely commercialized. However, there are also other types of detectors like quantum cascade detectors based on semiconductor technology, and quantum mobile infrared detectors based on inter-subband transition can produce extremely high photo response, which would be useful for high-speed communication applications. In terms of material, fiber, silicon, metal for plasmonics or 3-5 compound already been developed and investigated. However, in order to achieve the best system performance, as I mentioned in the last slides, there's still a need to continue to search for better device performance. For example, achieve a broadband operation, room temperature operation, compact size, low, which can be mass produced, low power consumption, low cost, photonic and optoelectronic components. And this could be possibly achieved by using new material system. And the 2D material system could be one of the options. Okay, so that's the motivation of our research. So I'm going to talk about our research on the development of photodetectors, like first a PtSe2 photodetector, and then a hybrid photodetector by combining graphene oxide nanoparticles with graphene, and also some research related to highly confined Phonon-Polaritons in 2D material, and also thin film of germanium for achieving highly confined Phonon-Polaritons. Of course, everybody knows graphene. It has very unique, several unique properties like high mobilities and direct dispersion curve, so that it can have a broadband photo response from UV up to the terahertz or even microwave region. Okay, so as shown here, and in the mid-infrared region, the absorption coefficient is higher than that in the visible range, which is 2.3%. In the mid-infrared region, because of free carrier absorption, the absorption coefficient can reach to about 10%. Okay, for monolayer graphene. And the graphene has already been developed into different type of optoelectronic devices in integrated photonics, optical applications, from tunable mode-lock fiber laser into polarization control, photodetector modulators, as well as in terahertz wave detectors, and potentially can also be applied into the mode-lock semiconductor laser. However, all these demonstration mainly demonstrate in the visible and the near-infrared region. While graphene has a really broadband photo response, it can also be extended into the mid-infrared terahertz region. So therefore, we aim to replicate the same demonstration also in the mid-IR and the terahertz region. Of course, certain challenges apply. So here, for example, we use a photodetector as an example. Photodetectors, in a simple classification, we can divide this into a photoconductive detector, where a thin film is used as an optical absorbing layer, thin film to absorb light. And once a photon incident on the thin film, electron hole pair generated, where if you apply a source stream, the electrodes to apply a voltage across the thin film, and then you can measure the current, and which relate to the photocurrent of the corresponding to the incident light, and then by measuring the photocurrent, you can derive the photon generated on the detector. So in this configuration, if you put a backgate, like metal contact, and gated the film, and then you form a so-called field effect transistor configuration. And the most of the, I would say, demonstrated 2D material photodetector is based on this configuration, IPET configuration. It has a relatively broadband photo response, high responsivity. However, the external bias is required, and it also has relatively large dark current. Another type of detector is so defined as a junction detector, where literally is similar to the photoconductive detector, but without external bias applied. So when the photon is injected, electron hole pair generated, and due to the built-in electric field, the electron and the hole are flowing into the different side of the junction. And if you connect it with external circuit, and then you can measure the photocurrent, and then derive the light, incident light intensity. Okay, it has a relatively high speed, low dark current, but also relatively low responsivity. So for graphene photodetectors, a number of devices has been developed over the years. The intriguing properties of a graphene is that it has a high mobility, and then the theoretical prediction of the response speed of such detector can reach to 100 gigahertz or more. However, because graphene only has one monolayer, and therefore the absorption is quite low, which has therefore low responsivities, about only tens of milliampere per watts. And people use plasmonic structures to enhance the photo response or using cavities, right, to enhance the absorption of the light in graphene. However, the responsivity is still quite low. And another approach is to use a so-called hybrid structure, where a nanoparticles is placed on top of the graphene layer, still in this IPT configuration. And here the nanoparticles is used as a light absorber. And because light nanoparticle has a strong absorption coefficient, so such configuration can give a really high responsivity. And however, the current demonstration using the nanoparticle that use can only absorb light in the near infrared region. Okay, so we want to build this mid-infrared photodetector in 2D material. Therefore, we look at the material possibilities that we can choose, and this shows a summary. And for the mid-infrared 2D material, basically graphene is one choice. However, it's limited by the responsivity, and the black phosphorine can cover literally up to around 3 micron. And recently, this arsenide phosphide was used to cover the wavelength range around the 3 to 4 micron. So here in this work, we first identify a new material PtSe2, and then we find out and discover that a bilayer of such material has a narrow bandgap that can cover in a wide wavelength range in the mid-infrared region, literally from around 10 micron down to the visible range. Okay. So this PtSe2 is similar to the other transition metal, the chalcogenide material like MOS2. However, through this first principle calculation, we found out that the bandgap of monolayer PtSe2 has a bandgap of about 1.2 eV, which is close to the near infrared. And the two layer of such material can produce an indirect bandgap about 0.3 eV. So that's correspond to wavelength bandgap to correspond to the photon energy about 0.3 eV, correspond to the wavelength about 4 micron. And the 3 layer or monolayer is basically a semi-metal, has a 0 bandgap. So therefore, we should use a 2 layer of such material for mid-infrared applications. And we collaboration with collaborated with Liu Zheng's group in the material science department. And by using different fabrication methods, we fabricate relatively high quality of such material. And then we found that the so-called chemical vapor transport technology can produce the best quality among other different methods. And indeed, then we fabricate a different device with a different layer thickness verified by AFM. And through the electronic measurement, IV curve characterizations, y-axis is current, x-axis is voltage. We found out indeed that the 3 layer of thicker layers has ohm contact, while monolayer has a relatively large bandgap. Therefore, you see this large band. For 2 layers, it has relatively linear curve, but still some banding right here. It shows that the bandgap of the material is narrow. And then from there, we fabricate the FET device based on this both monolayer PtSe2 and bilayer PtSe2 photodetectors. As expected, for monolayer PtSe2 detector, it has a large photo response at visible, some response in the near infrared. However, because of large bandgap, we don't see any photo response with infrared, mid-infrared light illumination at the 10 micron. On the contrary, if we use bilayer PtSe2 to build this FET device, we see a significant response in both visible and up to the mid-infrared region. However, based on the calculation, one interesting point here is that based on the calculation, bilayer graphene should have a 0.3 eV. So by right, this material should not have see any photo response at the 10 micron, because 10 micron close to 0.1 eV. And then based on that, we further investigate the defect contribution to the bandgap. And we found out that in the right figure, with only a few % of defects, in fact, the band structure can be dramatically changed with a much narrower bandgap, correspond to 0.1 eV. And then this provides us the opportunity that through defects engineering, we can engineer the bandgap of such material in order to cover a wider mid-infrared region. And this absorption spectrum show indeed the cutoff wavelengths can reach to 11 or 12 micrometers. That's the reason why we still see a good response at the 10 micrometer excitation. And here I show a comparison with other technologies compared to graphene. The responsivity is significantly increased, and it also has a large quantum efficiency. The detectivity of the device is not as good as the commercial MCT or HCT. However, such detectivity result is measured at the low temperature, and this is the room temperature measurement. I would say if this HCT is measured at the room temperature, then they have similar performance. And the further improvements can be carried out to improve the performance of the device, for example, by changing the dielectric environment, and also by doing surface engineering or using heterostructure 2D material. In fact, we recently already achieved such a device by cascading 2 layers of heterostructure 2D material to achieve through the interlayer transition mid-infrared photo response. And the responsivity is quite good. However, such materials still have 2 layers. So therefore, the absorption coefficient is still limited. Okay. So here we borrowed the idea from this Nature Nanotechnology paper from Copen's group in Spain. They use this hybrid structure, as I just explained. The advantage of such structure is that the nanoparticle has a strong absorption, therefore increase the responsivity. At the same time, this graphene layer on the bottom is used as a high-speed transport channel. So once the electron hole pair is generated, one of the carriers will be transferred into the graphene layer. And because here you apply voltage across the source and drain, and therefore the carriers in the graphene will circulate, right? And the lifetime of the other carrier in the nanoparticles have relatively long lifetime. Therefore, the carrier in the graphene can circulate many times before they recombine. So this can generate significant photo response, and in fact can produce a very high gain. In this paper, is demonstrated up to 10 million. Okay. However, as I said, it's only operate in the near infrared region because there's no narrow bandgap nanoparticle available. And what we discover or found out is that this titanium 203 nanoparticle, in fact, is a very interesting mid-infrared material. This material actually already investigated in 1960s, but not well studied on its optical properties. And we found out that different to titanium dioxide, which is a large bandgap material, and this titanium 203, because of the tangling of the bond in this 3D electron states, upper valence band can be created in the bandgap. So therefore, you can create a small bandgap in this titanium 03, roughly with a bandgap of about 0.1 eV. So therefore, this titanium 203 is a black in the visible region, or because the light absorbed. And through the absorption measurement, we can see the cutoff wavelengths indeed around the 12 micrometers. So that's exactly what we need. I'm going to, we work with Professor Tom's group from Sydney. to get the high quality material. And for such structure, one important part of the device is the carrier transfer from the nanoparticle to graphene. So unfortunately, the as-grown titanium 203 particle and the graphene are both p-type material. So that's why, based on this Raman peak observation, you don't see their shift, means there's literally no efficient carrier transfer from nanoparticle to graphene in as-grown samples. But the good part is that we have this back gate in the FET structure, so we can gate the graphene layer to make the graphene as N type of material. With that, we can have efficient carrier transfer between the nanoparticle to graphene. So this figure basically shows that through the Raman spectroscopy, we indeed can achieve such, observe such carrier transfer. And indeed, in the device fabrication, as shown in the middle figure on the top, by gating the graphene layer, if we gate positively, and then this is in the N-type region of the graphene, we indeed see the photocurrent generated, while in the negative voltage applied, we don't see such a photoresponse. Okay, so here the figure on the top right shows the photoresponse of such photodetector with a 10 micron laser illumination. Okay, it has relatively good photoresponse speed at around 1 millisecond. A very high responsivity beyond 100 ampere per watts across a wide range of wavelength region. This is limited by the laser that we have in the group, and we also characterize the noise level in order to determine the detectivity. So this can, at room temperature, this can reach 3 times 10 to the 8 value, which is also, I would say, a reasonably good number as a start. And as compared to the other 2D material-based photodetectors, this type of device, to our knowledge, it should be the first of such type that covered in the mid-infrared region with good responsivity, shown here. Next, I'm going to talk about the topic related to highly confined Phonon-Polaritons in 2-dimensional materials. First, in MOS2 material, Polaritons are quasi-particles in the form of electrodipoles coupled with photons. They can be formed in the form of electromagnetic wave at the interface between positive and negative permittivity materials. And the examples, for example, like plasmon polaritons that exist at the metal dielectric interface, or Phonon-Polaritons that exist in a polar substrate, where the substrate can provide the negative permittivities at the phonon resonance. Or another example is the exciton polaritons in the semiconductors. And here we look at these Phonon-Polaritons, and the study of such polariton and trace back as early as the 1950s, where this Pagel study and describe the Phonon-Polariton as the photons coupled with the electron dipoles originated from the lattice vibrations. So here, why we look at Phonon-Polaritons, because it provides the bound states of light for nanophotonic chip scale technologies, and especially the Phonon-Polariton can have a large momentum as compared to that of light in free space. Therefore, you can significantly shrink the phonon wavelengths, much shorter than the wavelengths of light in free space, and this could be useful for nanophotonics applications. Light matter interactions as well. So here we want to highlight that this highly confined we are talking about means the confinement up to 100, around 100. Okay, so that's our interest. And the Phonon-Polaritons, because of the relatively long diffusing time compared to the plasmonics, it has also relatively low loss, provide a relatively low loss platform for nanophotonics. And in the past, this Polariton has been well studied in a plasmonic platform, in the metal dielectric plasmons, hyperbolic metal dielectric plasmons, graphene plasma recently in both medium-infrared and the Telluride region. In the Phonon-Polariton platform, boron nitride hyperbolic material has been widely studied for achieving highly confined Phonon-Polaritons in the bulk boron nitride material. And very recently, very interesting and promising platform was demonstrated by Professor Thomas Hopner's group by using high reflex index GST, which is a phase change material on the quartz substrate to achieve highly confined Phonon-Polaritons. And they also, because the GST is a phase change material, they also show the tunability of such device. So I would say this is really the excellent work that motivated us to do the highly Phonon-Polariton research that I'm going to present later. However, at that time, our question is, such system, the eventual device performance is limited by the material quality at the nanoscale. Okay, so our question is that, whether we can, find a new system to achieve ultra-confined Phonon-Polaritons and also push the limit to the fundamental atomic scale in both the device level and also in the field confinement level. So we look at this three-layer system, and the substrate consists of a negative permittivity material and a thin layer of dielectric on the top, which has a positive permittivity and air. Just looking at the Maxwell equation of this system, we can derive the confinement factor, which is defined by the wave vector of the Phonon-Polariton over the wave vector of light in free space. And we can simplify the confinement factor into this formula, which consists of two terms. The first term relates to lambda over d, and the d is the thickness of this dielectric layer. And the second term is related to the logarithmic function of the dielectric function of that dielectric thin layer and also the substrate. So the key factor that determines the confinement factor will be the first term, lambda over d. So in a way, it shows that the thinner the thickness of this dielectric layer, the higher the confinement you can achieve. Okay, and here shows the simulation result. Lambda as a function of d. This is the operation wavelength of the light, and this is the confinement factor. So you can achieve like 1,000 times or even more. And we also calculate the loss factor in such system, which is determined by this beta prime over beta double prime. Okay, so as a function of the permittivity of substrate and permittivity of the dielectric layer. So in a way, it shows that we need to optimize the ratio between the two layers, and we need to have the dielectric and the substrate layer has high permittivity as high as possible, and also low loss in the mid-infrared region, and with exceptional uniformity with a super flat surface. So that's the task. So we identify in this case, then we propose to use silicon carbide as a substrate, provide the Phonon-Polaritons, and then you can use a 2D material in this case, because 2D material really guarantee high uniformity in a large area. Okay, and here we use a STORM system. I believe all the audience have a good knowledge about the such near field scanning optical microscopy system. That's a new spec system we use. Okay, and basically we need to measure the interference fringes of the Phonon-Polaritons launched onto the sample, which was formed by the forward propagating Phonon-Polariton and backward propagating Phonon-Polaritons. And silicon carbide air interface does support the Phonon-Polariton, but as you can see, the confinement factor is very low, less than 2. However, by just simply put MOS2 on top of such structure, we can significantly achieve highly confined Phonon-Polariton with a factor of 1,000 times, a few hundred times. And the loss of 2D material in the mid-infrared remain unexplored. However, in the literature, there are already some detailed studies has been investigated in the property of the 2D material in the near-infrared regions. So here, for example, it shows that many 2D material has a relatively low loss in the near-infrared region, which also show the trend into the mid-infrared region. The negative permittivity should approach to 0. So this gives us a confidence to further investigate the loss property of such material. And then we use a suspended MOS2 material, and through the transmission measurement, we characterize the permittivity of such 2D material. And we found that has a relatively constant large real part of the permittivity, 14, and relatively low loss in this whole mid-infrared region. Okay, and therefore we make such device and use the SNORM system to measure the near field imaging directly. And the figure in the middle shows very nice interference fringes. Using the same system under the same operation condition, we had a very difficult time to measure graphene plasmonics, with the same confinement factor because of the relatively high loss. So here, indeed, this Phonon-Polariton system has a relatively low loss, which allow us to do some comprehensive investigation. So here we can achieve the Phonon-Polariton wavelengths, 100 times smaller than the wavelengths of light in free space. And the extreme measurement, we can achieve the confinement factor up to 190. And we also see that by slightly tuning the excitation laser wavelengths by a few %, we can control or manipulate the confinement factor of Phonon-Polariton, from 20 times up to 100 times. So this gives us the flexibility of tuning through the excitation frequency, through the changing the excitation frequency. And then we measured several different devices with different thickness, and we plot this dispersion curve as a function, as compared to the theoretical predictions. Good agreement has been achieved, and then we fix the excitation frequency, and then we plot the Phonon-Polariton wavelengths as a function of the thickness of the dielectric layer on the top. Now we see a very nice linear fitting. So this should fit into this linear relation. L is related to the permittivity of the system. Okay. However, when we reach the thickness of this 2D material from 3 layer to below to 1 layer or bilayer, we indeed see some mismatch of the experimental result between the experimental result to the theoretical predictions. So one reason would be, the permittivity of the 2D material at the monolayer and bilayer would be quite different to that of the bulk material. And however, in the literature, unfortunately, we couldn't find the accurate and the detailed study about the permittivity of the 2D material, especially in the mid-infrared region. So if anybody in the audience are able to, either do comprehensive, quantum theoretical analysis or experimental investigations about these, properties in the monolayer and bilayer extreme, please do let us know so that we are happy to work with you to further investigate this part. And this platform is quite uniform, also applied to other 2D materials, and we explore different 2D material, and we see similar phenomena as to those observed in MOS2. Okay, and more importantly, as detailed down in this review paper by Joshua, Professor Joshua, Indeed, there are many other flexibilities in the scaling of the wavelengths, by choosing different polar substrate, and we can, design the system to at the different operation wavelengths. And of course, we need to choose a proper dielectric layers as the top contact layer. So, and then the next, we explore using CMOS compatible germanium material, because graphene still not really considered as a CMOS compatible material, while germanium has extremely low loss in the mid-IR. It has relatively large the refract index, and therefore can provide compact footprint. And more importantly, is a purely CMOS compatible material. And therefore, we allow us to achieve mass production of such germanium-based devices. Okay, so that's the reason we explore, changing the top contact layer, dielectric layer to be germanium. And here we, using E-beam lithography and the thermal evaporation to fabricate relatively high quality germanium on silicon carbide substrate. And laterally, this such system can also support highly confined Phonon-Polaritons. So here we fabricate several resonator devices to show such capabilities, and with a device dimension from a few 100 nanometers to a few micrometers, shown right here. And the interesting part is that we are not only observing the so-called sheet mode that has a resonance in the inside the cavity, but also along the edge. We call it edge mode. And such edge mode can have high momentum, higher than that of the sheet mode. And therefore, if we measure the confinement spot, as shown in this figure, on the top, in the middle, okay, we can see the confinement, can reach to, beyond the 200. So such system give a very high confinement of the edge mode, down to with a spot size down to around 50 nanometers. And we further investigate this system on the sensitivity of this germanium silicon carbide Phonon-Polariton wavelengths to the change of the interface compositions. Because when we look at such system, to accurately describe such system, we also need to consider the oxide layer of germanium, because germanium can be oxidized in the ambient environment. So therefore, in principle, we should consider like 4-layer structure. However, this system analysis is similar to what I have described in the MOS2 silicon carbide structure. And is also follow, through that, we do the calculation of the dispersion curve. And we measure the Phonon-Polariton wavelengths as a function of the thickness of the oxide layer as a function of time, okay? And then we can, from the result, we can review the sub-nanosecond sensitivity of these Phonon-Polariton wavelengths as a function of the change of this oxide layer. So even the oxide layer thickness change just by 1 angstrom, the Phonon-Polariton wavelengths can change in 9 nanometer, which is observable. So this result really give us the detection of the interface composition change at the bottom limit. It also shows the potential of using such a system for the detection of the chemical reactions, okay, especially at the interface. And the last, I'm going to talk about how we design a grating structure in order to launch surface Phonon-Polaritons. So the previous sample we use, previous examples we use tip to launch the surface Polariton mode. However, for efficient launching of a propagation mode, we can use a grating. So here we show such example, and here the grating period is 4 micron. Of course, when we launch the infrared wave into the grating, we naturally also form a localized mode, on the grating, which is, by the way, formed on the germanium on top of silicon carbide substrate. Okay, And here the figure C and D shows the dipolar mode and higher order mode, which shows relatively high Q factors of 100 and 200 respectively. And you know, this number is higher than those of a surface plasma mode in the same wavelength region under the same confinement and the same wavelength. Okay, so that shows the advantage of Phonon-Polaritons. And then such localized mode will be coupled with the propagation mode. So here the figure on the right, top right, shows such coupling. So as you can see at the frequency of 920 inverse centimeter, this is correspond to the dipolar localized mode, and around 890, this is a higher order localized mode. And this this yellow curve, red curve, and the green curve shows the dispersion curve of the surface of phonon propagation mode. And you know, they are coupled because of a relatively strong coupling. You know, you will see a mode splitting here, the Rabi splitting. So we get a good you know, number of Rabi splitting about 13 to about 13 inverse centimeter. Okay, at the same time, through such coupling, we can also tune the properties of surface Phonon-Polaritons in terms of resonance of wavelengths, which can really cover, you know, over like 24 inverse centimeter. By the way, the top left is the experimental result. And we also observe, we believe the first time, the coupling of this dipolar mode with a higher order you know, surface phonon propagation mode, although it's relatively weak, but indeed this is a mode here, which is also observed in the simulation. Okay. And in simulation, we also show that indeed, you know, when we change the grating period, we can see the mode property change from a dipole-like mode into more like a surface propagation mode. Okay, into the structure. So, okay, in summary, I have shown you, you know, two types of photodetectors. One based on PtSe2, which is a good performance, narrow bandgap, MIDI infrared material. And we also show that through structural engineering, we can, you know, use titanium 203 nanoparticles as a absorption layer combined with graphene for achieving high responsivity MIDI infrared photodetectors. And the improvement can be done through defect engineering and the dielectric engineering, for example, passivation of boron nitride or other dielectric layer to reduce, for example, Coulomb interactions, improve mobility, to further improve the device performance, or using van der Waals heterostructures, as just mentioned. We already have some results demonstrated, not shown here today. All into the photovoltaic mode operation, where the dark current can be significantly reduced. We also show you that by using just a very simple three-layer structure, using 2D material as a dielectric layer, we can achieve highly confined Phonon-Polaritons, and with ultra high confinement, up to 100 times or even more, and also demonstrated in the germanium-based CMOS compatible platform. And such device could be, you know, has the potential for high density optoelectronic applications. And with that, I would say, you know, there's still a large room for exploring 2D material in the mid-infrared and also in the temperate region, which I don't have time to say a few words about that, you know, to explain the detail. You know, such 2D material could be potentially very useful for both mid-infrared and temperate regions. You know, by developing, for example, photodetectors, modulators as well, polarization controllers, and even light source. And with that, I want to thank you for your attention. That's my team and the facilities that we have. And last, I take a minute to have a job advertisement. And so here in my group, we have 2 research fellow position available, and also PhD position available for those who are interested in exploring medium flat tapers photonics, or particularly on 2D material. Please feel free to contact me. Thank you very much for your attention. That's all.
Thank you, Gigi, for this great talk. It's now time for questions. I'll remember you can either write your question in full in the Q&A box and I will read it aloud, or you can just write voice and I will unmute you. Please, if you decide to write your question and if you want your name, me to read your name, write your name explicitly in the box. I'll actually start with the first question or comment. Can you please go back to the slide in which you showed that the experimental data don't fit the linear regression?
Oh, yes.
I see this happens for extremely small layer thicknesses. I would like to point out that we have seen that when you reach those kind of dimensions, non-local effects start to be important. We have seen how non-local effects with the coupling, with the actual propagation of phonon modes start to affect the results of nanolayers around few nanometers. There is a PRX from a couple of months ago in which you can find. So this could actually provide an explanation of why those results deviate from the local theory at small thicknesses. Okay. Do you have any comments?
So, yeah, it should be. Are you able to use this quantum non-local effect to calculate, precisely the dielectric function in this region? Is it possible using our model?
Yes. If you have, you need to have access to the dispersion of the phonons, but given that those are well-known materials, yes, you can actually use either different kind of approaches, both numerical and analytical, to get fairly precise results. We actually were able to quantitatively fit the dispersions in crystal hybrid made by studied by the group of Joshua Caldwell, and we obtained a quantitative fit. So I think that for, given that those are also well-known materials, it should be possible to get the quantitative results.
Okay, so I will read out the paper, and then if you need, I can contact you.
Second question. The effective area of the detector is determined by the active area of the 2D material. Antennas are passive elements that strengthen the interaction, but otherwise just take space. So for fair comparison of sensitivity, one needs to compare such a device with the classic photodetector with the combined area of the 2D material, active region, plus antenna, passive element. Could you please comment on what would be the corresponding figure of merit?
Yeah, so in terms of that, the detectivity actually is I would say of course I agree, with the comment, one cannot just use responsivity to, fully describe the performance of the photodetectors. I would say the best figure of merit will be the detectivity of the device. So with that, actually, both noise and also the dimension of the size of the detector already considered. So that's will be the fair comparison.
Okay. Next question: is the decreased noise of the silicon carbide layer relative to graphene related to uniformity?
In Phonon-Polariton work, is it?
I don't know.
Yeah, we use, I think the question related to the highly confined Phonon Polaritons. We don't use graphene, but using MIS2. Yes, so if you reach such a thin layer, so traditional method like demonstrated in GST or even germanium structure, there's still some surface roughness variations. And then you cannot produce ultra uniform such thin layer with 1 or 2 layer, or even 3 layer. So therefore, the 2D material give naturally such uniformity, and over the whole period. Even now with the growth, fabrication technology improve, especially using CVD, such material quality also improve. So which also allow us to fabricate large area of such device on 2D materials.
Thank you. Next question. Thanks for the great talk. Could you maybe motivate physically from where the high confinement achieved by thin dielectric layers on polar crystal substrates originates?
No, so I think I explained here the main, the main part is this, the physics is really here. This is the, why we achieve a highly confined Phonon Polariton. In terms of high performance, I won't see, indeed, such a system provide extremely, low loss or extremely long propagation length. That's not exactly true, because these 2D materials still have some loss, as I show in this characterization, in this measurement, right? And of course, the additive effect, the scattering all happen. But this, the main thing I want to show here is the highly confinement property by using 2D material. That's the unique thing. And then the other materials, other than 2D material, cannot be used to implement such property because of a fabrication challenge. You cannot fabricate such a thin layer on the polar substrate.
Thank you. Next question. What is the coupling parameter G for the hybrid propagating and localized mode?
Can you say again, what's the coupling strength?
I think it means that, yes.
Yeah, so in the experiment, we show that, the coupling correspond to like 13 inverse centimeter. This experimental results. The rapid splitting. In terms of coupling strength, I'm not so sure what kind of unit you want to use, but the rapid splitting basically describe this coupling strength. I think it's if I remember correctly, it's a good one. Okay, it's not the the best one. In compared to other system, it's not, but it's very good number already. So shows, I would say that's in the strong coupling region, not ultra strong, not ultra strong, but strong coupling region.
I will make another comment myself. We had a paper with Stefan on strong coupling between surface propagating Phonon-Polariton and the modes localized in the pillars. Is the coupling from this figure? The coupling seems to be of the similar order, of similar intensity. Do you agree?
Yes.
Next question. How is the repeatability of the graphene T203 photodetector?
Repeatability, graphene, okay. Graphene nanoparticle, repeatability, how should I address that? Repeatability means, of course we have fabrication errors, the student, fabricated device at the lab. Let's assume there was no fabrication errors. I would say yes, all the device works, as long as there's no like human errors, because it's a quite straightforward process. We just have a graphene, which we use CVD, graphene, and then deposit this nanoparticle fabricated by my collaborators, and then just disperse on the top surface. So I would say all the device works, but of course, device has a various device performance. It's not exactly the same performance. That's true.
Is there any other question? Well, if not, with this, we are done. We all thank Professor Wang again for this truly great talk. Thank you very much. And we wish to thank you all to have followed us through this first season, and we hope to see you back in October. Details of the talks will be announced, as always, on my Twitter account and on the MIDI page on Facebook. Thank you all, and see you in October.
Okay, thank you everybody. Thank you.